Okay, this video is for an analysis of hydrogen peroxide, and so I'm going to do kind of an introductory part one of this lab. You'll need to do the part two by yourself and make sure you know how to do it. So anyway, the first thing is what you'll be given is you'll be given this equation, but this equation right here is not the entire equation for this lab. What it is, it's kind of a scaled down equation that has the major ions that are in play. And what you're going to need to do is turn this into a balanced equation. All right, because right now maybe it looks balanced. I doubt it is, but it's not. But you can't just balance it in terms of saying, hey, there's one iron here and one here, because electrons are transferred. So you got to do it like this. So the way to do it is to write the half reactions for the things being oxidized and the things being reduced. So first of all, I'm going to take this manganese and I'm going to find that 4 times the negative 2 is negative 8. So the oxygens are contributing negative 8. Okay, but the overall ions is minus 1, so the manganese must be plus 7. All right, so I can write the half reaction for the manganese. Manganese is plus 7, and then we're always going to add electrons to the more positive side, and so the manganese goes to plus 2 over here, so you're going to have to add 5 electrons. Okay, then if you look through, it's pretty easy to see that the iron is plus 2 here, and then it's going to iron plus 3 on this side, and you're going to have to add 1 electron to that side. All right, so the manganese is being reduced, so that's the reduction half reaction, and the iron is going to be oxidized. Now, anyway, there's a rule that the electrons being lost in an oxidation must be equal to the electrons gained in a reduction. And you can see 1 does not equal 5. So what you got to do is you got to multiply this whole equation by a factor of 5, which means up here, to balance this equation, you'd have to put a 5 there and a 5 over here in front of the irons. And then the oxygens are 8 here, but there's only 1 there, so you'd put a 2 there, then you'd put an 8 here, and that would balance the equation. Okay, but the important part is that it's KMnO4, which is actually potassium permanganate, reacts in a 1 to 5 mole ratio with the iron. We're going to use that a little bit later, but just remember that it's a 1 to 5 ratio. Okay, so anyway, then if you go down and you read this lab, and you have to do problems. Well, this is the lab procedure that we followed, and then anyway, I guess I cut off the number 4 here, but number 4 is calculate the molarity of the KMnO4. And so I'm just going to make up a number and say that it took around 12.5 milliliters. Now, the thing is, I made this stuff, and it was supposed to be 0.02 molar. But your job is to standardize it. And to standardize it means you're going to do a titration to figure out how close to that 0.02 is it. Is it right on or is it a little bit off? So I'm just making up a number that if we were to add the KMnO4 out of the burette tube, how many milliliters would it take from the burette tube to end up reacting with all the iron compound? And so if you remember from the last thing that we did, it goes in a 1 to 5 ratio. So there's, for every 1 KMnO4, you have to have 5 FEs. All right? So anyway, here's kind of how this all goes. All right? What the students did that did the lab, they started off and they put 0.40 grams of this iron-containing compound. Like I said, the equation that I gave you was very simplified. It didn't have all these ions and things in it, that is spectator ions. So they put 0.40 grams of ferrous ammonium sulfate, and I don't really like to write the whole formula, so I'm just going to abbreviate it, ferrous ammonium sulfate. Now, if you're ever in grams and you're trying to do some sort of titration problem, you always got to change to moles. So 1 mole of ferrous ammonium sulfate and the molar mass is 392.13 grams. Okay, then what you're going to do is you're going to do the mole ratio. And so the mole ratio is 5 moles of iron, so 5 moles of ferrium ammonium sulfate to every 1 mole potassium permanganate. Alright, now back on that net ionic equation, the potassium was a spectator, so it wasn't included. Alright, and so what's going to happen is you're going to do the math and you're going to get the moles there, however many moles, because that's the unit that you're going to be left with. Oops. Okay, don't want that. So that's the unit that you'll be left with. And so you'll get so many moles. Okay, and that's moles of KMnO4. And then you're going to divide that by how many milliliters it took. Well, not milliliters, but you have to change it to liters. But how many liters it took to react with all the iron. Okay, so to react with this many grams of this ammonium, which was basically the ammonium, ferrous ammonium sulfate was basically the iron. You have to take the moles divided by the liters, and so you have to change this to 0.0125 liters. I had to move the decimal 3 spots from right here. I just changed that into liters. And if you do that, you'll get that the molarity, of the KMnO4. All right, now I'm not gonna work out that problem. I'll let you work that one out. But that's how you would set it up. Now I want to show you what I want you to do. So what you're going to do is you're going to do part 2. And so with part 2, the first thing that you have to do is you have to figure out, write the half reactions. So okay, so you're going to write the half reactions and then you're going to balance this equation. All right? And so basically what we're doing an oxidation reduction between the hydrogen peroxide and this potassium permanganate. And you're going to come up with the overall balanced equation, okay, without the spectator ions. All right, and then you should be able to do number 2. You should be able to do number 3. All right, but number 4, you'll need the lab data to do it, and so I put that in there. So anyway, so let's say that you put 1 milliliter. So this is what we did in the lab. So in the lab, we put 1 milliliter of the H2O2 in the flask, and then we started, and then we had to add some acid to it. That's the way this potassium permanganate works. It works in the acidic environment. So we added some acid and some water. That's not that important. But then what we did is we titrated it, okay, until it turned a light pink, and that's how we knew when to stop the titration. So let's say it takes 16.4 milliliters of the KMnO4. All right. So now you know that it took 16.4 milliliters of the KMnO4, and you should, if you do the calculations on the previous page, you should have a molarity of the KMnO4. Now, it was supposed to be 0.02, but I think it's a little bit off. Okay, so you got to use what the calculation here, what your molarity is here. Okay, and you're going to plug that in right here, because then you'll know the molarity of it. And so if you know the molarity of it, remember that molarity equals moles over liters. So you'll know that it's so many moles, whatever you calculated on the other page, of KMnO4 to 1,000 milliliters. All right, so then you'll be in moles, and basically you're going to be solving this, and you're going to be solving it for, at the end of this problem, I want you to end up with grams of H2O2. That's what I want you to end this problem with. All right, so I don't know if that gives you some clues or not, but that's what you would need to do. All right, that's it for this video. you can try to do that problem.